eliminate harmonics in the inversion process, we go for controllable inverters, where we have our switches being replaced by the controllable switches. So in these controllable inverters, we'll try to incorporate one more stage where we have output voltage to be 0 instead of just being positive and negative. So now we know that when you turn on your switch 1 and switch 2, then your load resistance is being exactly connected across your source, and you get output voltage to be same as your DC input voltage. Now the other stage that we know is when you turn on your switches S3 and S4, then you have your output voltage negative terminals being connected to positive of the source, where you have output voltage to be same as negative of the source voltage. Now instead of these two stages, we'll also get two more switching sequences, where after this, instead of directly going for 3 and 4, we'll turn on the switch 1 and switch 3. When you turn on these two switches, your output voltage is going to be same as this, where it is a short circuit. So now when you turn on your 1 and 3, then your output voltage is going to be 0 here. Now let's say after this stage of negative voltage, if you turn on your switch 2 and 4, then you will have your output voltage being connected to a short circuit, where your output voltage will be 0. Means you have two cases where you can attain an output voltage of 0, and you have two cases where in one case you get your output voltage to be positive, and the other case you get your output voltage to be negative. Now if you try to follow a sequence, then you can get this particular waveform as your output voltage within the duration of your fundamental frequency. That is, here you have your positive voltage where you turned on your S1 and S2, and then you have a 0 output voltage during which you have turned on your S1 and S3. We know that when you turn on your 1 and 3, then your output voltage is connected to a short, so your output voltage will be 0. And then you have negative output voltage where you turned on your S3 and S4. That is where you have this particular case. And then you will have your output voltage to be 0 here, where you turned on your S4 and S2. So this is where you are changing your switching condition one switch at a time. So here you have 1 and 2, then you move from 2 to 3. Now you have 1 and 3 where you moved from 1 to 4. Now you have 3 and 4 where you moved from 3 to 2. And again, you now moved from 4 to 1 here. So this is where one switch at a time you have been modifying, and you are getting this particular voltage as an output. So now, if you follow this switching sequence, then what will be the harmonic distortion? What will be the harmonics for us? Now, if you try to see the Fourier series expansion of this particular output voltage and observe the harmonic distortion available in this output voltage, then we can, same as the previous case where your output voltage can be represented as a function of a Fourier series where it has an offset and the combination of cos and sine functions. The condition of not having an offset, since it is symmetric about the time axis, is valid even in this case. So your value of A0 is still 0. Now we also know that this particular waveform still follows the half-wave symmetry, so your values of A and R 0 means you don't have any cosine waveforms embedded into your output voltage response. Now it is indicating that even this voltage can be represented as a sum of various sinusoidal voltage components. Now if you calculate the peak values of the sinusoidal voltage for different frequencies, it is the same expression where your voltage exists from your alpha to pi minus alpha. So this is being repeated later on. So now if you look at that and substitute your output voltage from alpha to pi minus alpha, then your Bn, that is the coefficient of the peak value, will be now depending on the values of alpha. But we still get the values of Bn to be 0 when n equal to even, and the values of Bn are now 4VDC upon n pi cos n alpha when n is odd. So indicating that this output voltage do have the sinusoidal voltages, then each sinusoidal voltage need to be only odd. Now we do have this output voltage being represented as a function of sinusoidal voltages which are of odd frequencies. That means odd harmonics, 1, 3, 5 and so on. So now if you look at that and substitute, then we say that my Fourier series is telling me that output voltage is now function of various sinusoidal voltages with a peak value of Vn, where Vn is non-zero only for odd values. So now if you know what is Vn, we figured out that the value of Vn is 4VDC upon n pi cos n alpha. Now if you closely observe, the values of alpha can be modified to change the peak value of sine voltages. If your value of alpha can be changed to modify the peak value or adjust the peak values of the sinusoidal voltages, so indicating that the harmonics now can be controlled by changing the values of alpha. Now how can you control the harmonics? By changing the values of alpha. Let us say now I have selected my value of alpha to be 30 degrees. If your value of alpha is 30 degrees, then you can write down that V01 is 4VDC upon pi cos alpha. That is cos 30 degrees for us. Now V03 is 4VDC upon 3 pi cos 3 multiplied by 30 degrees. Now you know that this is cos 90. The value of cos 90 is 0, that means this is equal to 0. Whenever you represent this waveform as a fundamental voltage as well as third order harmonics, fifth order harmonic and seventh, ninth order harmonics, then you know that this third order harmonic peak value is 0, which is indicating that here, compared to the previous case, your value of a third order harmonics, here compared to the previous case, the value of the third order harmonics is becoming 0. So in a way, by following this switching sequence and selecting the value of alpha as 30 degrees, you will get the peak value of the third order harmonic to be equal to 0. In a way, you are eliminating the third order harmonics in your output voltage. When we say that we can eliminate the third order harmonics by following the proper switching sequence, means that we initially had an inverter where we just had a positive and negative output voltage being obtained using two different switching conditions. And then we had the output voltage, which is almost a square waveform. And we observed that we had a fundamental voltage. You can see that in this, the sinusoidal voltage we have here is the fundamental frequency, and we have a third order frequency of voltage, and we have fifth order frequency of voltage, and we have seventh order frequency of voltage and ninth order frequency of voltage. So when you combine all that, the fundamental third order, fifth order, seventh order, ninth order frequencies, then the output voltage you get will be close to your square wave. Means the square wave that we have here is the combination of the fundamental third order, fifth order, seventh order, and ninth order, and so on the frequencies. But when you follow a different switching sequence, where you have 4 different switching conditions, and you could get positive, negative, and 0 voltages at your output, then this particular waveform, when you select your alpha equal to 30 degrees, then this is what is your output voltage. Means you have your output voltage width being shrunk, and you can see that it is represented as a function of a fundamental frequency, that is V01, but you do not have the frequencies that corresponds to third order harmonic. That is, you after first order, you have fifth order frequencies, then you have seventh order, and you can also calculate and see that you have no ninth order frequencies. Now when your third and ninth order frequencies and the respective higher order frequencies are being eliminated, your output voltage that you got with the width being shrunk is much closer to the sinusoidal voltage when compared to a pure square wave that we have in the first case. So it is clear indication that by changing your switching sequences, you are able to eliminate the harmonic distortion in your output voltage waveforms. This is what motivates us to go for the pulse width modulation, and we have seen how do we eliminate third order harmonics by adjusting the width of the output voltage. So now we wanted to know if we can have different widths of the output voltage in the conversion process, then can we eliminate the harmonics of the different order? Now, if we can eliminate harmonics of the different order, how do we select the switching sequences or switching widths of the output voltages? Now, for an example, you have an inverter where you controlled your switching periods and modulated your output voltage widths and achieved this particular output voltage waveform, where you have the width of this particular waveform to be 2 alpha 1 and the starting point of this waveform middle width is alpha 2. So now if you wanted to know what kind of harmonics can I eliminate by choosing what values of alpha 1 and alpha 2, then first we need to express this output voltage in terms of a Fourier series and make the sinusoidal components corresponds to the harmonics to be eliminated to be 0. Now let us have a Fourier series expansion of this output voltage. Now again, even this output voltage is symmetric about the time axis and it doesn't have any offset. So we can say that the value of A0 is still 0. Now you can also see that this output voltage do have a half-wave symmetry, which is indicating that the value of AN is exactly equal to 0. And you can also say that your output voltage can now be represented as a function of multiple frequencies of sine waves. Now, what are the peak values of those sine waves? We know that it can be obtained by calculating the value of Bn. So, if you substitute this particular output voltage waveform and calculate what is Bn, you still get the value of Bn to be function of alpha 1 and alpha 2. Bn is 4 VDC upon n pi multiplied by 1 minus cos n alpha 1 plus cos n alpha 2 only when n is odd. When your n values are even then the Bn equal to 0. That means you do not have even order harmonics even in this case. You'll have only odd order harmonics. So let us say your n equal to 1, 3, 5, 7 and so on. That's what is happening. For example, if I want to eliminate third order and fifth order harmonics, because we are always interested in eliminating the harmonics that are close to the fundamental, a higher order harmonics may not be of a bigger problem. So now if you want to eliminate third order and fifth order harmonics in this case, then for n equal to 3 and n equal to 5, I don't want to have any Bn. Means you want your Bn to be equal to 0 for n equal to 3 and n equal to 5. So this is what is the condition. If we want to eliminate the third and fifth order harmonics, then Bn for n equal to 3, you want that to be equal to 0. And Bn for n equal to 5, you want that to be equal to 0. The peak values of the third order sinusoidal waveform and peak value of the fifth order sinusoidal waveform, you are expecting that to be equal to 0. If you want that to be 0, then what should be your values of alpha 1 and alpha 2? Then if you solve these two equations, where you have two unknowns and two equations, you get to know the value of alpha 1 is 17.8 and alpha 2 equal to 38, which not have third order and fifth order harmonics if you choose the values of the width and the timing according to alpha 1 and alpha 2. So this is where we can see that the more are the pulses that you get in your output voltage, which are well articulated according to the elimination of the harmonics that you want to remove, then you will be able to get better sinusoidal voltage as an output in the inversion process. What is the motivation for the pulse width modulation? we learned that by adjusting or modulating the width of the output voltages, we can eliminate the harmonics in our output voltage. So the pulse width modulation is a technique where you try to eliminate the harmonics in your output voltage by modulating or adjusting the width of the output pulses in your inversion process.